Now that we know how to solve more complicated circuits using KCL and KVL, I'm going to show you a new method that's actually a really neat application of both KCL and KVL that acts as a shortcut for solving circuits. So if we have a circuit like this, suppose we have a resistor here, a resistor here, a resistor here, a resistor here, and let's put in a current source. Let's let this be R1, R2, R3, and R4. Okay, so if we have a circuit like this, in the last module we might have used superposition to consider one source at a time. Once we do that, we would find R equivalent. We basically have to do that twice since there's two sources in here, so it takes a long time. With this node voltage method, we save so much time because we don't have to find R equivalent. So the way it works is the first step number one is we want to label all of the nodes. Okay, so here's a node, I'll label it V1. Here's a node, we'll label that V2. I'm going to go ahead and label the sources too. I'll call this VS and I'll call this IS. Now the next step is we need to designate a reference node. The reference node is almost always ground, so I'll put that in parentheses here. So if we make this be our reference node, that means that we're going to be writing all of our node voltage equations with respect to this reference node, and I'll show you how that works. Now the third step is we're going to use KCL to write current equations. And we want to write those current equations at each node. So by KCL we know that the current coming into this node is equal to the current that splits down this branch and this branch. So if I label this as, I'll just call this I1, I'll call this I2, I'll call this I3. So then that means that at node V1 that I labeled, the KCL equation I have is I1 is equal to I2 plus I3. Now the second node at node V2, I have I3 coming in. I'm going to have an I'll label this I4 that takes the path down this R4 resistor. And then I have this I source that actually comes into the node also. So by KCL, the sum of the currents going in is equal to the sum of currents going out. So at this node V2, I have that I3 plus IS is equal to I4. Okay, so that was my third step, was to use KCL at each of these nodes to write the currents coming in and out. Okay, so then after I've done that, the fourth step is from these current equations, from the KCL equations, I'm going to use Ohm's law to write voltage equations. Okay, so since I have resistors, I'm going to basically rewrite these two equations to be voltage equations in terms of voltage and resistance instead of current. And then once I've done that, the last step is I just solve for all voltages. Okay, so let me show you how we would change these current equations into our node voltage equations. Okay, so at node V1, so let's look at V1. My current equation was I1 is equal to I2 plus I3, right? So I1 I'm going to replace this with the difference of the voltages divided by the resistor between. Okay, so I have that I1 is equal to Vs minus V1 over the resistor between R1. And the reason why I'm doing Vs minus V1 is I'm starting from the higher potential and going to the lower potential, and basically we're just going to follow the direction of the arrow that our current is going. Okay, so if we had a current that was going this way, then we would do V1 minus Vs. But since our current starts at Vs and goes towards V1, we're going to do Vs minus V1 divided by the resistor between, which is R1 in this case. Okay, so that's our I1. I'm going to replace I2 with, I2 is going to be V1 minus my reference node. The voltage at my reference node is just 0. So this is going to be V1 minus 0 over the resistor between, which is R2. Okay, and then the last one, the last current that I need to replace at this node, I got I1, I got I2. Now I'm going to replace the current I3 with V1 minus V2 over the resistor between. Okay, so I have I3 is equal to V1 minus V2 over R3. And just like in the previous case, since the direction of my current is going this way, I'm going to do V1 minus V2 instead of V2 minus V1. Okay, so we're just going to basically go with the flow of the direction of your current arrow. So now I have my three currents. These three currents are related by this equation. So what I can do is I can take my KCL equation at node V1 and I'm going to just replace it with these voltage and resistance terms. Okay, so I'm going to replace from my equation I1 equals I2 plus I3. I'm going to rewrite this as, in place for I1, I put Vs minus V1 over R1. In place of I2, I'm going to put V1 minus 0, which is just V1 over R2. And then in place for I3, I'm going to put V1 minus V2 over R3. Okay, and this is my first node voltage equation. Okay, so we did this at node V1. Let's do the same thing at node V2. Okay, so the node V2, at node V2, my KCL equation that I've already developed was I3 plus IS is equal to I4. So we want to replace the currents with the voltage and resistance equivalent using Ohm's law. So I'm replacing I3 with V1 minus V2 over R3. V1 minus V2 over R3. So that's the resistor between. I'm going to replace IS. I don't need to replace IS because this is going to be given to me. This is my source current. So this is going to be some value that's designated ahead of time because this is an independent current source. So I don't need to replace that in my equation because this will just be a constant. And then my I4 I'm going to replace with V2 minus 0, that's my reference node, over the resistor between, which is R4. V2 minus 0 over R4. So that means that this equation, from this equation I can write my node voltage equation, which is going to be V1 minus V2 over R3 plus some IS constant is equal to V2 over R4. And this is my second node voltage equation. Okay, so if this is my first node voltage equation, this is my second node voltage equation, I now have two equations and two unknowns. Because what will be given is Vs, I'll know R1, I'll know R2, I'll know R3, and I'm trying to find V1 and V2. So I have two equations, two unknowns, V1, V2. From here you can use substitution to solve. You can also use linear algebra. And for more nodes, I can show you some linear algebra methods later on in the module for how to solve larger systems. So in the next video, I'll show you a specific example for using node voltages to solve a circuit like this.